Okay, welcome back everyone for the last day of the workshop. We are happy to have Emil Martinec here for the first talk, and he'll be talking about brain stars and black holes.
Thank you. Thank you to the organizers for what's been an enjoyable conference so far. And what I'd like to tell you about today is a culmination of a series of works that I've been engaged in over the last few years, trying to understand heavy microstate structure and holography from a bulk perspective, and using in a series of works with my collaborator Yoav Zigdon and also my collaborators in the microstate geometries community, using effective field theory methods to describe heavy microstates in situations where there are ADS core of the geometry, and combining that with information that we get from exact worldsheet realizations of some of the branes that are involved in sourcing those heavy microstates. And I should say, and much of what I'll be talking about today is this latest work with Zigdon, which really provided for me sort of a moment of clarity about the role of all of these constructions, complicated constructions of bubbling geometries and superstrata and so on and so forth. What is their role? What place do they hold in the constellation of heavy states that we get in holography? And I was especially happy to see this to the finish line. You get to my age, moments of clarity become increasingly rare, so you're happy when they come along. And so what's the arena? It's this well-trodden territory of three-charge microstates built out of one branes, five branes, and momentum. People usually think about the background fluxes as being Ramon fluxes, in which case there's a weak coupling gauge theory picture of bound states of branes that if you then dial the coupling to strong coupling, it becomes some warped geometry. But that process of going from weak coupling, while it's straightforward to enumerate the microstates at weak coupling, what they look like in the bulk at strong coupling is still a bit mysterious. And so as a warm-up exercise, I'd like to consider the situation where we study heavy BPS states that are not black holes. And the reason they're not black holes is that we keep the charge sources that are sourcing the background separated in space a little bit. Okay, so because it's matter and it's separated in space, if we separate it in space enough, there won't be a horizon. And so the horizonless geometries that people have been going on about over the last dozen or so years, maybe 20 years in some cases, 25 years, those all fit into this paradigm of things that are not black holes that cap off in some kind of deep ADS throat, simply because you've separated the constituents a little bit in the transverse space. Okay, so we'll spend most of our time talking about that and then speculating somewhat what happens when we take those things and we poke them a little bit away from BPS, what's going to happen. Okay. So just to summarize what's in this last paper, we were able to construct exact three-charge. So first of all, the duality frame that I like to work in is not the usual one of Navier-Schwarz fluxes D1, D5, et cetera. It's the S-dual frame in which we have Navier-Schwarz fibranes and fundamental strings sourcing NS flux that make an ADS3 or ADS2 near source geometry. So in that frame, we've been able to construct an enormous collection of three-charge supergravity solutions that are themselves bound states of two-charge constituents. Okay, so we take the two charge constituents. The NS5P constituents were enumerated by Lunin and Latour in work 25 years ago. F1P goes back even further to work of Dabelkar-Harvey and others in the 90s. And what we're going to do is we're going to make bound states of those things. And the momentum is carried on the Brane sources as chiral momentum waves. And it'll turn out that you can find explicit supergravity solutions where you allow that chiral wave profile to be completely arbitrary. And so you can study those backgrounds even in asymptotically flat space and get explicit solutions. But as well, you can take various decoupling limits where you decouple phi brane from the ambient flat space or take an ADS3 limit. We'll work in the phi brane decoupling limit simply to avoid unnecessary notational baggage. But I just want to point out that it's not essential. And then the T-duals of these geometries are the so-called superstratum geometries that have been the subject of a lot of work in the supergravity community by Bennett Warder and their collaborators. These solutions show something that used to be said about gauge gravity duality is not quite true. It's true that if you study excitations near the vacuum, that in some sense the branes get dissolved in flux. You have some nice smooth ADS geometry where the branes aren't apparent. But if you excite the system sufficiently to make a quite heavy state, the branes start re-emerging, especially in these slightly Coulomb branch configurations that I'll exhibit later. Okay. And so this is sort of a question of this gets at the question of if you're going to make a black hole, we know, from the gauge theory that the horizon in the gauge theory is associated with deconfinement in the non-abelian dynamics of the gauge theory. And so the thing that's going on here is when you separate the branes a little bit, you make those non-abelian constituents a little heavy, and they decouple. And the geometry abelianizes, and that abelianized geometry has a geometrical counterpart. Okay, and then what we'll see is that directly in the bulk, the process of horizon formation will be the reemergence of those non-abelian degrees of freedom when we shove the branes together. Okay, so when the branes are a little bit separated, we'll see that the geometry caps off at a finite redshift and finite proper distance depth of the throat. And so, as I say, these states are more akin to stars, because a star is something that sort of lives outside its Schwarzschild radius, because all the constituents are puffed out to some characteristic size that's bigger than the horizon scale. Okay. The typical near horizon geometry, these will be some sort of an ADS2 throat, whose depth is controlled by the size of the sources. Okay, so indeed, when the sources are compressed to a sufficiently small region, that throat gets increasingly long, and eventually a horizon starts to form. We'll also see that because the chiral wave profiles we can put on the sources are arbitrary, the generic such chiral wave is some collection of left-moving, some thermal gas of left-moving excitations. Okay, and so the thermal properties will lead to some kind of random character of the geometry that's sourced by these wiggly strings and fibranes. And that dynamics of perturbations around those BPS configurations is manifestly chaotic. How chaotic is one of the open questions I'll list at the end. Okay. And in particular, there's a kind of a breathing mode. If I take the sources and I compress them a little bit, well, I said that the depth of the throat is controlled by how separated the brane sources are. And so if I compress the brane sources, I make the throat deeper. And so there's a kind of a breathing, there's a breathing normal mode of this brane star, okay? That when the throat gets sufficiently deep, shares a certain vague similarity with the kind of Schwarzian dynamics that appears in black hole, ADS2 black hole physics, where again, the Schwarzian modes are oscillations in the proper depth of the horizon. Okay. Now, because the background is being sourced by Nova-Schwarz fibranes, the holographic context is something called little string theory, where you can take a decoupling limit of Nova-Schwarz fibranes, and what you see is not something that's ADS geometry, but the throat geometry sourced by the fibranes is something where you have a sort of a cylindrical throat with a linear dilaton where the coupling is running to strong coupling in the IR. Okay. And in that context, the way of understanding the BPS black hole entropy formula, which is the sum of, which is the product of the square root of the background charges, is to say, okay, the entropy is being multiplicatively enhanced by the presence of the other charges in the bound state. And for perturbative strings, the N1 and the P we understand because when you bind momentum to a string, if the string is wound N1 times, the quantum of momentum is fractionated by a factor of N1, and so the entropy is enhanced relative to what you would get from just a gas of massless particles to being enhanced by the square root of the product of the winding charge and the momentum charge. And then when you add fibranes and as fibranes to the mix, it's believed that what the little string is that's living inside the fibrane is something that's a fractionated fundamental string. So if I had N1 units, and the fractionation is by a further factor of the number of fibranes, so that if I have N5 fibranes, then a string that has winding N1 that's bound to that fibrane has a little string winding, where the string, when it enters the fibrane and binds to it, separates into N5 constituents, and so the total winding of little strings is N1, N5, and so there's a further factor of N5 fractionation, and that's a qualitative way of understanding this entropy formula. Okay. But that fractionated string dynamics is strongly coupled because that little string has an effective alpha prime that's governing the black fibrane entropy, where essentially the little string has a fractionated tension. Its tension is also N5 times smaller than the fundamental string tension. And string perturbation theory is predicated on the perturbative string being the lightest tension object in the system. So anytime you have something whose tension is lighter than the fundamental string, the system is intrinsically strongly coupled. Okay. So we're going to try to avoid that strong coupling issue for as long as possible, as I said, by separating the fibranes in space. So an M-theory cartoon of what's going on is to lift, say, 2A string theory with fibranes to M-theory. The fibranes become M-fibranes. The fundamental string is a membrane that's wrapping the 11th dimension. And when you have N5 coincident fibranes, and you take that wound string and you push it on top of the fibranes, the M2 branes can separate into strips because M2 branes can end on M5 branes. Okay, and that's the fractionation phenomenon. The winding of the M2 brane has been broken up into N5 strips, each one of which has its own independent motion within the fibrane world volume. Okay. But if you separate the fibranes in the remaining transverse directions, what happens, and then you go back down to the type 2 string theory limit, what you're doing is you're squeezing the 11th dimension in space. But if you've kept the fibranes separated, now those strips stretched between the fibranes become D2 branes under the dimensional reduction back to 2A. Okay, and so depending on whether the strings are, the M fibranes are lined up on top of each other or they're separated in space, these fractionated constituents are either fractionated fundamental strings or some kind of stretched D2 branes. When they're stretched D2 branes, they're heavier than fundamental strings, and therefore they decouple from the low energy dynamics. And in that situation, then the non-abelian dynamics can be consistently decoupled from the low energy physics. Okay. So let me first talk about just what is the decoupled geometry of fibranes, and then later we will add the other two sources, the strings and the momentum. Okay? So if we have just 5 branes, okay, the entire geometry is controlled by some harmonic function. Okay? So the fibranes are located at some points in the transverse space xm. The superscript flat is to indicate that I'm doing this in asymptotically flat space. So the geometry that's sourced by this harmonic function, it appears as a warp factor in front of the transverse Cartesian, what's sometimes called the base space of the transverse space. Okay, and then that harmonic function warps the geometry, right? If I go very close to the sources, the 1 over r squared in the harmonic function cancels the dr squared plus r squared d omega squared of the flat transverse space. And so the proper distance coordinate is dr over r, some kind of logarithmic coordinate down this throat. Okay, and the angular S3 saturates at constant size. So the throat geometry very near the sources is some kind of cylinder, S3 times r, where because the dilaton also involves this harmonic function, the dilaton is linear in that logarithmic coordinate. So it's sometimes called a linear dilaton throat.
Sorry, actually, maybe I should ask slightly earlier. When you separate these 5 branes,
yes,
then the fundamental string becomes D2 brane.
The fractionated string that's stretched between them, but there's still fundamental strings that can live in this throat.
Right. Yeah. But then the stretched between the
those become
D2 branes.
D2 branes, that they become heavy and decoupled.
Right.
So it's consistent to just talk about perturbative string theory living in this throat.
Right. Yeah, I'm confused by one very elementary thing. Somehow, it seems like when you separate the D5 brane a little bit, you're not doing very much. But somehow this doubly boson suddenly generate 1 over G string dependence. Because D2 brane have this 1 over G string dependence.
Yeah.
Somehow, is there any simple way to understand that?
It's coming.
Okay.
Coming. Okay. So the idea of the decoupling limit is, if you're far away from the poles in the harmonic function, then it's effectively constant. And so the dilaton saturates to its asymptotic value and space is flat. Okay, and so the characteristic size where you go between asymptotically flat space and this cylindrical throat is a distance scale which is square root of n5 in string units. Right, because if I'm not resolving the individual 5 branes, it looks like I just have something that looks like n5 alpha prime over r squared. So it just looks like I have some cylindrical throat of size root n5 in string units. Okay, and so now, and then, somewhere far down the throat, you reach the scale at which the branes are separated. And then you start resolving individual 5 brane throats. And so if I trusted this geometry and went arbitrarily far down it, I would see n5 little throats, each of which is angular size 1 in string units. Okay? So the thing that keeps, naively, if you're a supergravity person, naively you would say, oh, I can resolve things down to the Planck scale, right? It's just, when I get some kind of quantum gravity effects. But that's not true here because the graviton is a string. And you have to ask yourself, do strings fit in various places in the geometry? And one of the results of these exact worldsheet solutions that I mentioned on the first slide is that these throats that are size 1 in string units are too small for a string to fit into. And what the exact solution tells you is that a string reaches this scale of the 5 brane separation, and it says, I don't fit into any of these other little throats in the geometry, and so they just reflect back. And so if you study some kind of wave packet that's running down this dilaton throat, it has no transmission amplitude, it just has some reflection phase, and the phase governs the time of travel. And the time of travel is just telling you how deep this point is down the geometry. Okay? And the decoupling limit is to take G string to 0, holding this ratio fixed. Okay, so we scale down. So what we're basically doing is we're separating. We're making the separation between this region where you're opening out onto asymptotically flat space and this point in the geometry, you're separating those by an arbitrarily large proper distance, okay? So from the point of view of somebody who sits here in the geometry, a fixed proper distance from this region, and you take this scaling limit, what's happening is that the top of the throat is being pushed off to the UV. And the entire geometry then just becomes this cylindrical throat. And the only scale in the problem is this scale, the scale of the separation of the fibranes in string units. Okay. And that's the so-called double-scale little string theory that Givon and Kutuzov and their collaborators have been working on for almost 30 years. Okay, so the decoupled geometry, just as usual in this sort of game, is a scaling limit in which the 1 in the harmonic function drops out. So the harmonic function now looks like this. I drop all the flats decorations on all of the coordinates. Okay, and as I said earlier, this effective, squid structure in the infrared is not part of string theory. String theory doesn't see anything that looks like that. String theory sees something that nicely and smoothly caps off at the scale of separation of the fibranes. Okay. And so this is not a picture of a Euclidean geometry. This is a picture of the spatial transfer space to the fibranes, where I have some angular S3 and some radial coordinate which caps off smoothly. Okay. But I do have a self-similarity of this fibrane throat. If I rescale the VEVs of the fibrane, Coulomb branch Higgs expectation values by some factor, what I'm doing is I'm moving this cap, this effective cap in the geometry up or down the throat. So there's kind of like a breathing mode of the solutions which governs where is the cap in the geometry. Okay. And if I look at something like these, what I would call W branes, the D branes that stretch between the fibranes, they are things that start off at one fibrane, and because D branes do sense down to the Planck scale, so the D branes will fit into this little throat, but all they can do is come up that throat and dive down another throat, okay? So when you plug all that structure into the dBi action and you say, what is the mass of that stretched D brane? It turns out that there's a cancellation between the warping of the geometry and the running of the dilaton. So that if I look at any D brane that's stretched in the transfer space, those two factors exactly cancel one another, and the mass of the D brane is conveniently just the Cartesian distance between the fibranes. And this factor of G string drops out because of the way that I rescaled the Higgs VEVs. Okay, and that ratio just defines what I'm calling the rescaled coordinates. Okay, so strong coupling is fibrane separation is 1 in these appropriately rescaled, conveniently rescaled variables. And so that defines what I'll call a non-abelian scale. The scale at which that's the scale at which these stretched D2 branes, which are the little strings, in the strong coupling phase, it's the scale at which those D2 branes tension become as light as fundamental string tension, and then perturbation theory is starting to break down.
I'm confused by one remark you said earlier. You said earlier somehow in string theory you cannot resolve those legs, but I thought that those legs are just string scale. You should be able to resolve them.
With D branes, okay, but the D brane, the dynamics on the D branes is open strings, and open strings also don't fit. Okay, so if you try to shove, some D brane down this throat, it essentially has no dynamics. It's essentially once it gets in here, it's been absorbed by the fibrane, and it's indistinct from the gauge theory dynamics on the fibrane.
So, so you say if you look at the string sigma model, then you just see a smooth cap off.
Yes.
But somehow, then, yeah, I'm still not sure I understand under which precise regime you see those legs.
So you don't see them. So what I'm claiming is that if, from the point of view of effective field theory, which we'll get to in a minute, there's an effective field theory of strings in the throat, and then there's an effective dynamics of the fibranes, which is some abelian gauge theory, because the fibranes are separated and we're looking at energies below the scale of the Higgs VEV. Right. We should just look at some kind of U1 to the N5 gauge theory on the fibranes. And so that's the effective field theory we'll write down in a moment and solve for the resulting bulk geometry.
So that is the one which will be added to your string theory, ordinary string theory sigma model discussion.
Yeah, I need to include the dynamics of the fibranes as an explicit source.
Right, as a separate, yeah.
As a separate source, yes.
I see.
Okay. So now let me indeed add the other two charges. And so the setup we're going to consider is we want bound states, right? So the first thing I want to do is bind the fibranes together. And an easy way to bind the fibranes together is to compactify everything on a T5. And we're going to put chiral waves on the fibrane. So in order to be BPS, all those chiral waves have to be parallel to one another. So let's pick out one circle, which I'm going to call S1Y. And all the chiral waves will live on that circle. Okay, and then we put a twisted boundary condition on that circle that says instead of having N5 individual fibranes, we have one fibrane that wraps that circle N5 times. Okay, and the convenient thing that the chiral waves do, if you put chiral waves on the scalars which are saying where the fibrane is, so these are the things which are getting the expectation value. Okay, if you make those scalars sufficiently highly excited, then, as I was saying, you have some kind of wiggly profile to where the fibrane is, which is essentially some kind of thermal excitation of these scalars. Okay, and so these thermal scalars are randomly walking around because it's thermal. And so as I go around to the next winding of the fibrane has randomly walked somewhere else in the transverse space. And so the more excitations I give it, the further apart things are separated, and the more self-consistently weakly coupled it is. Okay? So that's our control parameter, is the level of excitation of these scalars on the fibrane. Okay? And the color coding in this diagram is just to guide your eyes to what the connectivity is. So successive windings are neighbors on the colors wheel. Right? So I go from red to orange to yellow to green to blue to red. And that tells you how this thing is connected. Okay, and then you can do the same thing for fundamental strings. Take some fundamental strings. There's some other things that are wiggling around in this geometry, and also having some, you can also decorate them with some chiral wave profile. Okay, and so we'll consider a single wound fibrane and a collection of wound strings and ask ourselves, can we solve the BPS equations that result? So there'll be explicit supergravity BPS equations with explicit sources coming from the strings and the fibranes. And the lucky result is that we can write down a solution in complete closed form for arbitrarily specified profiles. And so ordinarily I wouldn't bore you with the details of solving supergravity field equations, but in this case I feel it's quite instructive. So let me go through a quick summary of how it goes. So we start with an effective action, which is bulk supergravity, and some standard Polyakov action for fundamental strings, which would be winding this Y circle. And some similar effective action for the fibrane. So the fibrane has some, gauge theory coupled to some scalars on its whirl volume. The T4 is playing no role. The fibranes just wrap the T4 and not excited in any particular way for the situations that we'll consider. And so we can just dimensionally reduce everything on the T4. And so when you do that, the supergravity becomes 6-dimensional supergravity. And the fibrane reduces to another string in 6 dimensions. It's just that it couples to the magnetic dual of the 2-form that the string couples to. So you can think of it as a magnetically charged string. So we have electrically and magnetically charged strings in 6 dimensions. All of them carry chiral wave profiles. And we want to ask, what is the supergravity field equations? Okay. So it's been known since work of Gutowski, Martelli, Real, a long time ago, that there's a standard form that the geometry takes in such 3-charge BPS backgrounds, in which all of the metric and anisymmetric tensor and dilaton field coefficients satisfy harmonic equations. So this is the lovely feature of these particular backgrounds in 6 dimensions, as opposed to solving, like, half BPS equations in ADS 5 cross S5, where the field equations, the BPS field equations are still nonlinear things. Right? This is shown by the Lunin-Maldacena construction. Here, they're just, they really are solve the harmonic equation in 4 dimensions. It's that trivial, okay? Another useful feature is that for these particular 2-charge sources that we're putting into the background, one of the harmonic 1 forms that appear all over the place is just 0. It's not sourced by either of these string sources. And so that's a simplification. Okay. Another thing to know is that, again, it's useful to double the antisymmetric tensor field content because we have both electric and magnetic strings. When you write the world volume Lagrangian, this fundamental string couples electrically to the two-form potential, and the phi brane couples electrically to the magnetic dual potential. So in order to write down the world volume Lagrangian, you need to couple it to a gauge field. The gauge field needs to be the dual gauge field. Okay. Okay. In particular, then, that duality relation between the two-form potentials in 6 dimensions leads to a set of duality relations between various coefficients that appear in the solution. So in particular, the electric coefficient in the 6-form potential is related to the magnetic term in the 2-form potential and vice versa by a duality relation. And then these coefficients are also related to each other by a self-duality relation. And similarly for the electric potentials. Okay. And color coding will be that green is strings and blue is phi branes. All right, so now we have to start solving sourced harmonic equations. And so the first thing to solve is what is essentially the Gauss law for these two sets of strings. Okay? So there's a Gauss law for the magnetic strings. Okay, so remember Z2 is this coefficient that appears in the warping of the geometry. That's the harmonic function, right, which was the NS5, sourcing the NS5 throat. Okay? So that solves a harmonic equation, looks like this. And the harmonic function I was writing down before is just the solution of this harmonic equation with delta function sources. Okay? But where the string is varies as I go along the y circle because I have this randomly walking source. And so, you know, where the pole is in that harmonic function is something that's wiggling chaotically as I run along that circle. Okay? And similarly for the strings, they have their own Gauss law equation that they satisfy. And in this case, if I'm only taking the phi brane decoupling limit, I keep the 1 in that harmonic function. And if I want ADS3, I take a further scaling limit, which decouples this 1, and then I just get harmonic functions with no constants in them. That's the limit everybody usually takes to go to ADS3. Okay, these 1 and 2 forms that appear in the B field are neatly packaged into a combination that appears in the field strength of the B field, which turns out to be a self-dual form in 4 dimensions. Okay. And its solution can be written in closed form, again, in terms of the wiggly profile of the phi brane. And similarly for another electric 2 form that gets sourced by the fundamental string. So far everything's being written explicitly. Various coefficients in the solution are being written very explicitly in terms of what the strings and phi branes are doing, okay, what the sources are. And at this level, the strings and phi branes don't talk to each other. They each satisfy their own Gauss law. And the strings don't enter the phi brane Gauss law, and the phi branes don't enter the string Gauss law. Where that enters is in the next layer when you want to solve for the harmonic function in the metric that tells you about the momentum that's being carried along the y circle, the third charge, as well as the angular momentum that's carried by the solution, the S3 angular momentum. Okay? And, okay, so those get some understandable delta function sources, which is that if I have a string, okay, the string has some energy momentum tensor. So I just take the Polyakov action and write down what the induced energy momentum tensor is in space-time that's coming from this string source. Then it's just some delta function source. So here, for instance, for the string, it's what you would write down from as being the 2-dimensional energy momentum of these scalars x, but remembering that the strings are living in the phi brane throat, so they get a warp factor coming from the phi brane throat. And because everything's electrically magnetically dual, there's a completely equivalent dual thing, which is the energy momentum delta function sourced by the magnetic string, which is the phi brane. But then there are also bulk sources to the energy momentum tensor, which is because I have both electrically and magnetically charged objects. Each have their own Gauss law, so they source bulk electric and magnetic fields, and so there's a Poynting flux, E cross B, or some six-dimensional version of E cross B. Okay, so there's some bulk source as well. Okay, but the bulk sources are completely specified by the harmonic functions I've already solved for. So these are some completely explicit sources, again, in terms of the wiggly profiles. And so, okay, I have a completely well-specified source in terms of these wiggly profiles, and then, just, some tedious exercise of saying, okay, what could the residues of the poles possibly be? And, you fiddle around for a bit and you get some answer. Okay. Again, completely specified in terms of your separation from where the wiggly sources are. And similarly for the angular momentum harmonic function. Okay. So you get some geometry. The geometry, as I said, is completely specified in terms of completely known harmonic harmonic with sources. Okay, and the sources are completely specified by what the string waves, magnetic and electric string wave profiles are. And because there are poles associated with where the sources are in those harmonic functions, if you're a supergravity person, you said, I don't like this, it's some singular geometry. Okay? But I just told you that when the fibranes are separated from each other, strings don't see that geometry. Strings see some kind of capped geometry, capped by how well separated these windings of the source are from each other. And the more highly excited I make it, the more separated they are, and the more shallow the cap is in the geometry. Okay, and then similarly, the harmonic functions that are sourced by the strings have some poles where the strings are. That's some complete artifact of treating the string classically. And as soon as I quantize the string, its wave function is going to get smeared out over scales that are at least in size alpha prime. And so those singularities are just resolved by perturbatively quantizing the string. So the claim is that perturbative string theory is completely fine, with the maximum value of the string coupling determined by what is the value of the dilaton in the cap. Okay.
So far,
so will there be any consistency condition on this FV and XV, or they're just completely arbitrary?
So the consistency condition is just that you as you're wandering along, you want to ask, like, what's the closest approach of two strands of fibrane somewhere in the geometry? And I'm arguing that they're well separated generically, but you could worry there might be some special places where they come close to each other. And the answer is that doesn't happen. It's essentially because as I slice things in Y, the sources are essentially like random walks, okay? So if I plot what is the probability distribution of the separation of two fibranes, it's governed by random matrix statistics. These source profiles, if you like average over the ensemble of all possible, excitation profiles, you find this sort of like the average source density for the fibrane is Gaussian. So it's some kind of like Gaussian random walk. And so if you ask, like, what is the pair separation of the eigenvalues of the fibrane, which is where they are, it's essentially governed by some random matrix statistics. Right. And so if you ask, like, how much of that, how much of the probability distribution is sitting down here where the fibranes could be close to each other, the answer is it's like 1 over n. So the places where there could potentially be some place where string perturbation theory is starting to break down is 1 over n suppressed.
Yeah, I see. Yeah, but in your equation, those functions, they are arbitrary.
Yes.
Yeah, they're just arbitrary.
That's right.
They're just integration constants. Yeah.
Yeah. Well, there's a specification of what background you have.
Yeah.
Okay. Okay. You can do all this explicitly if you specialize to some very coherent configuration, where the fibranes and the strings each just have one mode excited and excited macroscopically. And then if you only excite one mode and you excite it macroscopically, then essentially what's happening is that the source is executing some spiral, some helix. It's like leading Reggie trajectory, if you like, for a string. For a 5 branes, such a string is the province of some worldsheet gauged Wess-Witten model, so it's just completely exactly solvable. This is the work that I've been doing with Masai and Turton over the recent years. And so because there's an exact worldsheet theory, it's manifest that there is a consistent string perturbation theory where the dilaton in the cap of the geometry is governed by what is the separation of the strands of the helix. Okay. As I was mentioning earlier, we can ask, if we want to ask what is not some highly, and I should say, that highly coherent source where the 5 branes are running around a circle, that's the thing that's related to the superstratum geometries that people, supergravity people have been studying in recent years. Not in this duality frame, in a slightly different duality frame where we T-dualize along this direction, and if somebody's interested, I can explain it to you, but let me not dive down that particular rabbit hole. Just suffice it to say, put a pin in the observation that every microstate geometry that's been studied in supergravity over the last few years under the rubric of what are called superstrata is living in this ensemble of things I just described for you in some T-dual language. But since T-duality is a symmetry of string theory, I've described it for you even though I've used some different variables. It's the same solution. And so it fits within this framework. Okay. Now, if I ask the question...
Can you just repeat that? So you're saying superstrata are not more general than these?
Superstrata are a subset of these.
Okay. I thought superstrata depended on functions with 2 variables. Here you have only, you had only functions of these f of v and whatever. You had many functions of that, but they were functions.
And I have the possibility to have many fundamental strings. So what the 2 variables of the superstrata is, you say, what do you do there? You start with some 2-charge solution, and then you add the 3rd charge as some kind of back-reacted momentum wave. And the 2 variables are the quantum number distribution of those waves that you're dumping in the geometry. So in my duality frame, that corresponds to dumping in a collection of fundamental strings with a distribution of winding numbers instead of momentum eigenvalues. And so it's the same data presented just in a package differently.
But it's somehow still you imagining doing string field theory in this background or some such thing because you have an arbitrary number of strings.
So I bypassed, so the hard part about superstrata is you need to solve the wave equation in the 2-charge geometry. And so for the wave equation to be solvable, it needs to be separable. So you need to choose some nice, particularly symmetric background, namely this nice helical source. So in that background, the wave equation is separable, and you can back react it and so on. So what I've done here, when I say the strings are being solved classically, is that if I T-dualize that, I would be putting in some kind of semi-classical momentum waves. What is the semi-classical momentum wave? It's the WKB limit of the wave equation, where I replace the wave by a particle traveling a null geodesic, and I back react it exactly. So that, I was glossing over some of the details that when I say I'm describing superstrata, I'm describing effectively WKB limits of superstrata.
Right. So there was still a special. Well, anyway, you seemed like you violated the "there's no such thing as a free lunch" theorem, and.
Well. There isn't. So what this is all making very clear is that there are no horizons here because I'm describing these, in order to describe things that, classically in supergravity self-consistently without strong coupling problems, I had to separate the sources. Okay, but the black hole horizon is only forming when I shove the sources back together, compress them inside their Schwarzschild radius. So that's why I say these, the moment of clarity was that all the things I'd been studying with Ben and Warner over the last 10 years, they're not black holes. You shouldn't think of them as black hole microstates. And the claims that were being initially made, that we would replace the ensemble of black hole states by some set of horizonless geometries was a distraction. That these things are logically distinct. They're in some different part of the configuration space. Okay, and okay. So if we want to get a handle on, okay, if I have these random sources I can ask statistical questions like, what does the typical one look like? And one way of addressing that question is to say, okay, let me take the ensemble of all the wiggly profiles that, that they're classical solutions, and classical solutions form a phase space. So I can average over that phase space and ask, what is the ensemble average of all of these geometries I get? Well, they're all harmonic functions, so I just superpose harmonic functions and I get some harmonic function. Well, they're sourced harmonic functions, so I get the average of the source. And what I was saying before, that the average source is a Gaussian density with some width of the Gaussian. The width of the Gaussian comes from the random walk statistics. And it leads to this averaged harmonic function. And when you ask what is the width of the Gaussian, it's coming from the fact that if I'm exciting the fibranes with some momentum excitations, there's some n which is associated with the level of excitation of the magnetic string. And that's some thermal walk, and thermal walk has square root of n thermal wavelengths in the length of the string. And so if I ask how far spread out is the thing, it's the square root of the number of steps in the random walk, and so that's n to the 1/4. So there's some magnetic string length where the G string has disappeared from the fibrane tension because I've taken the scaling limit. Okay, and so there's some magnetic string length, and then it's n to the 1/4 and pi's and 2's and 3's. Okay, and so that sets the depth of the cap self-consistently in terms of what the typical excitation profile is. And so we do the same thing for the strings. Then you end up with a geometry that looks like this. So before I was plotting some kind of throat cylinder, which was the angular S3 and the radial direction. Push the S3 aside, it's still the same thing that's governed by what the fibranes are doing, so it's some kind of capped cylinder. We should be asking instead what the Y circle that everybody's wrapping is doing, okay? So asymptotically, that's some fixed radius, call it Ry. And as I come down the geometry, at some point I reach the charge radius of the strings. If Ry is big, then the strings are much heavier than the momentum excitation, so that's the hierarchy that's being set. And so the first thing when I come in radially is I reach the charge radius set by the strings. And now the strings are starting to back react. The non-constant piece of the string harmonic function is starting to dominate. Okay, I get attracted to an ADS3 geometry, because that's the geometry that's sourced by the decoupling. That's the attractor geometry of strings and fibranes. Okay, and then eventually I come into the place where the momentum harmonic function starts back reacting on the geometry, and the momentum is pressure, and that stabilizes the size of the Y circle. So now the Y circle, instead of continuing to shrink, as I continue to go into the infrared of the geometry, it's some stabilized circle. And so my angular geometry is T4 times S3 times S1. They all have constant sizes as I go into the further infrared of the geometry, and I just have some ADS2 with all the rest of this angular space fibered over it. And okay, but the length of this ADS2 region is bounded above by this non-abelian scale, because if I try to make that throat, how do I make this throat longer? I make it longer by compressing the fibrane source to make the cap deeper. So I can only do that so far before I reach the scale where the non-abelian W brane excitations start kicking in, and then all hope is lost because the fibrane dynamics become strongly coupled. But everything, short of that, all the things that look like this, which, as I say, include all the superstrata, are under control. Okay. Now, on the agenda for this program is to start looking at near BPS dynamics. And for that, there's a sort of a standard approach that one does in BPS dynamics. Again, if I have electric and magnetic sources, your sort of mental map for what to do follows from thinking about the same problem in 4 dimensions, where I think about, instead of magnetic and electric strings, I think about magnetic monopoles and electric charges. And if I have magnetic monopoles, the near BPS dynamics of magnetic monopoles is to start with the BPS configuration, which is just monopoles that are statically sitting at points in their transverse space, and ask what is the Yang-Mills-Higgs geometry that's sourced by those magnetic monopoles. That yields some kind of background. And then I can give a slight, there are collective coordinates, which are the locations of the monopoles. Okay? And so there's a nonlinear sigma model you can deduce by taking the Yang-Mills Lagrangian and expanding it in terms of small velocities for those collective coordinates. And what that gives you is a nonlinear sigma model whose target space metric is the metric on the moduli space of the BPS solutions. Okay, so the BPS configuration that I just described for you should be some kind of metric geometry for non-BPS, near non-BPS excitations of this system. So I go back to the effective action that I started with. It depends on some metric in B field and dilaton. I just solved for you the metric, the B field, and the dilaton. So I just plug it back into the effective action. And this is what you get. So it depends on, so there's some terms I had before, the T4 excitations of the strings, which I'm kind of ignoring for simplicity, but they're just free field dynamics. This is some flat metric on the T4. Okay, and then there's the free field dynamics of the fibranes. If I didn't have the strings, that would be what there is. So the Lunin-Matur solutions are derived by quantizing the left-moving modes as if they're just free harmonic oscillators. Now when I add the strings, okay, there's some nonlinear addition, which is, again, the strings and the fibranes are interacting with each other through their coulombic and other forces that they're sourcing. And so that appears here. And so it's exactly what you would expect, that when the fibranes and the strings are relatively stationary, then the velocity in this relative separation coordinate is 0, and the action is 0, and so that's the energy is 0, and that's the BPS bound. But even if I make them have left-moving excitations, as long as the only excitations are left-moving, then the right-moving derivative is 0, and I'm still on the BPS bound. Now, if I have left movers and right movers, if I take all the left-moving thermal, highly excited thermal gas, and I add a little bit of right-moving excitation, now all of a sudden I've raised the energy above 0, and I have some slightly non-BPS thing, and it does whatever it does, but it looks like an interesting system to study. So, okay. And you can say a couple things about it. So this smells like a simplified version of what people used to do in very early days of just after Stromann-Waffe. The question was asked, okay, we have this string, this effective, long string that's carrying all of the BPS entropy. And near BPS thing to do to it is to give it a little bit of right-moving excitation. People actually studied the absorption and emission of energy onto such a long string and compared it with the Bekenstein-Hawking entropy absorption and emission coefficients and got an exact match at leading order in low energy. So this is like that. It's smelling very much like that. I have a bunch of strings, except the strings aren't the maximally fractionated strings. I'm missing this factor of N5 in the fractionation by separating the strings and the fibranes. So it's very similar in spirit, but it's short in the entropy by factors associated with N5. But it's something which, it'll be interesting to see how it plays out. The other thing to mention is that these wiggly sources are thermal, they're random, and so the metric and the B field that the D coordinate is sitting in is essentially a random environment. And so, if I'm studying dynamics in random environments, it tends to be chaotic. And so it's almost guaranteed that this near BPS dynamics is going to be chaotic. And the interesting question is going to be how chaotic, and what are the Lyapunov exponents and the OTOC, everything that people have been doing for the last few years. Okay. I fully expect that there will be opportunities for this 5-brane star to collapse if we kick it enough. And as I was been saying all along, the way that happens is that you take these source profiles, and if you just compress them, if there's some way that the 5-brane can offload momentum so that it de-excites by, say, transferring some of its momentum onto the strings, then, the 5-brane is carrying less momentum, so it's less puffed out, But since the amount of puffing out is controlling what's the depth of the throat in the geometry, the system gets a longer and longer throat. Eventually, it reaches this non-abelian scale, and that I would claim is the place where you should expect horizon formation. Okay. Now, you can go back and do the same calculation that I did before, estimating what is the mass of one of these stretched D branes between the 5 branes. And it turns out that this conspiracy of cancellation between factors in the metric and dilaton continues to hold in the full 3-charge background. If you allow the D branes to co-move with the wiggles on the 5 brane, then it's still just the Cartesian separation of the branes. Okay, even in this much more complicated setup. Okay. Returning to this very simple example where we just excite a single mode on the sources, we can play with the parameters of the source distribution and ask ourselves, what is the depth of the throat? Where does the ADS2 region cap off? And what is the proper distance from the place where the ADS2 starts to the cap? So that's some proper distance I'm calling L. Okay, and so what is that L in units of the ADS2 scale? It's just the ratio of some charges, in which one factor is the extremal entropy, and then the rest are some factors which are, you can convince yourself, are always smaller than 1. So the cap is always smaller than the cap, sorry, the ADS2 region has a length which is always bounded above by log of the extremal entropy. Now, and that's being just done by some bulk calculation and consistency, et cetera, demanding that there's no non-abelian 5-brane dynamics. For those of you who've been keeping close track of the JT gravity literature, there's a lovely calculation by these folks from a few years back, asking in JT gravity, you have some ADS2 throat. And in this, so what I've been describing is approaching some kind of black hole formation threshold along a line of configurations, a path in configuration space along the BPS space, okay? These folks did some other calculation, which is, let's look at ADS2 black holes and start dialing the temperature down to approach extremality. And okay, and so at some point, so there's a proper depth from the UV scale with the top of the ADS2 throat to where the horizon is, okay? And at some point, when you keep lowering the temperature, you reach some scale at which black hole thermodynamics breaks down. That was this landmark paper by Preskill et al. In '91. And that scale was reproduced in JT gravity calculations as the scale at which JT gravity fluctuations become large. And you have to take in the quantization then of JT gravity, which you can do exactly. And when you do that, you find that there's a proper length to the throat from the UV scale to where the horizon is, which is again log of the extremal entropy. So things that you get from looking at taking the extremal limit of non-extremal black holes is matching things that you get from these explicit BPS geometries approaching the black hole threshold along the BPS line, or BPS manifold, I should say.
Sorry. Yeah, maybe
I have missed something earlier. I thought this L extension. Yes, can you say it again? Where this L extension AXT come from?
My L throat.
Yeah.
Is just I pick some point in the geometry is capping off here.
Right.
Right. The poles in the harmonic function are being smoothed out at this scale.
So
I'm asking the question: what is the proper distance from?
Oh, right.
From up here to down here. And the down here is governed by the 5-brane harmonic function at this scale. So I'm just measuring the proper distance in the metric geometry I started with between those 2 points. That's what I'm calling L throat.
Yeah, I see.
Okay, and so I claim it's log of these 2 scales that are set by the charge radii. But this scale is set by the charge radius, and this scale is set by the where you're starting to enter the source distribution. Okay. Good. So
that scale you have there just does not look familiar. In particular, I thought it was supposed to depend on the moduli at infinity. You decoupled them because everything was BPS, so that way you
because
had
I've entered an ADS2 attractor region.
This is true, but now that you look at near BPS excitations, you're sensitive to slight departures from that, and those slight departures, the scale of those is set by the scale that you had thrown away when you did BPS. And therefore, it's supposed to get back in again somewhere. If you look at near BPS, that scale.
Yeah. I mean, I'm very interested in understanding whatever can be understood of the spectrum of throat excitations in this geometry that I've specified for you. I think that's a very interesting. It's somewhere high up on the list of things to do. But before getting there, one thing I can do is to ask, okay, what's happening in the Schwartzian is that the Schwartzian modes are controlling fluctuations in the depth of the horizon, the proper depth of the horizon. Okay. On the other hand, this cap, which is setting in somewhat before the horizon, its depth is being set by the transfer size of the source distribution. Okay, so fluctuations in the depth of the cap are controlled by some kind of breathing modes of the sources. And so if I just take all of my sources and I rescale them by a common factor, I can take this near BPS effective action that I just wrote down for you and plug in a common rescaling of all of the sources. And what I get is some collective mode whose Lagrangian is very Liouville-like, except in the place where you would see the curvature of some kind of background two-dimensional geometry, you instead see the divergence of the dilatation current of the sources. But it's similar in spirit, and it's like the natural mode to study whose dynamics you would want to study, and it would be interesting if one could make some further connection between this collective mode of this five-brain star, this sort of like breathing oscillations of the five-brain star. Do they somehow merge onto Schwartzian modes as you get close to the black hole threshold? Now, okay. So ideally, one would want to follow things through completely and say, okay, when we reach this horizon scale, there's some kind of non-abelian excitations. D strings have become light, and some non-abelian five-brain dynamics takes over. Well, already that's interesting because it's showing in some bulk description, not just waving one's hands by saying, oh, deconfinement in the gauge theory sort of matches order one, the scale of the black hole threshold. Here you're seeing it very explicitly in some bulk description that when the depth of the throat becomes of order the scale at which a horizon should form, non-abelian dynamics in the gauge theory on the five-brains is the thing that's getting liberated. And as an effective field theorist, I would say, okay, I have new light degrees of freedom that weren't in my Lagrangian when all the brains were separated, and that to follow things into the black hole regime, I should add those light degrees of freedom which are becoming liberated. And so this is some argument that the thing that is controlling near BPS black holes in this context is little string theory dynamics, the dynamics of five-brains. Is in this duality frame intrinsically bound up with the black hole structure. And so if there was some kind of effective Lagrangian for little string theory along the lines that people were studying 30 years ago, then I would argue that the microstructure of the horizon is that. Some kind of membrane-like object which is sitting at the horizon, which is catching stuff from the bulk and emitting it in some unitary way. And I'm not going to say anything about black hole interiors because I'm doing effective field theory, and arguments about what's going on inside the horizon is sort of outside the domain of the particular effective field theory I'm writing down. Okay. So let me just summarize and then conclude with a list of what I think are interesting questions. So I've tried to argue that five branes provide an interesting example of gauge-gravity duality in which, in the particular setting that I've described, one can study both brane dynamics and its geometrical back reaction all in the same setting. And you can see the degrees of freedom that are responsible for black hole entropy get liberated when you start to enter the black hole phase. The things that people have been studying that are horizonless are in this brane star regime. So they're not black holes, but they're interesting because they're sort of adjacent to black holes. Okay. And the big question is, does this picture of brane dynamics persist into strong coupling, right? So if I was Bob Wald, I would say, oh, you guys are crazy. All of this structure you're talking about at the horizon, unstable to collapsing into some singularity, and you never see it again. So the question is there some mechanism that keeps that stuff supported at the horizon scale so that it's available, right? In order to resolve the information paradox through this sort of thinking, you have to have that structure available at the horizon. And that's basically what the heart of the fuzzball paradigm is that all of that structure of the black hole microstates is available at the horizon and not stuck way inside at some singularity. Okay. So what are the open questions? Well, I gave you an example of estimating this non-abelian scale when you reach that non-abelian scale for these simple single mode coherent solutions. I think that's robust, but the estimation of where that scale kicks in for the generic solution hasn't been done yet, but that's close to being finished. The near BPS dynamics, what are the chaos properties? Lyapunov exponents, ATOC, Thouless times, all the usual stuff. This breathing mode dynamics. In the case of the Schwarzian is well separated from other modes in the throat. Here, there are going to be all kinds of other throat excitations because of the different wiggles of the sources. And so the question is like, when I get to the deepest throats, how well separated is this breathing mode? Is it sort of universal and decoupled? Or does it couple to all of the other stuff that's going on in the star? Is there a fluid dynamics approximation? Can I really write down some kind of energy density, charge densities, momentum densities, et cetera, and just talk about some kind of stellar fluid dynamics? What is the holographic map? That's known for superstrata, and I said superstrata are some subclass of these things. And so the question is and it's the subclass where the strings don't carry any momentum excitations. There's an enumeration of all of the superstrata that corresponds to. And so the question is, can that be extended to the case where the strings carry momentum excitations as well as winding? What is the entropy? It's certainly more than it's bounded below by the superstratum entropy. It's bounded above by the black hole entropy. And so it's somewhere in between. And so what is it? I have some guesses. Okay, and then what happens when we deconfine these non-abelian excitations, and is there some useful little string near BPS effective field theory? So let me stop there, and thank you for your attention.
Thank you, Emil. Any questions? We have 5 minutes for discussion.
So if I want to extrapolate your picture a little bit, can I think somehow, say, if you just in the black hole regime, you want to say maybe that black hole can be understood by somehow if you are able to somehow go into to the horizon, then you replace the horizon by some coinciding five branes, and if you can understand the non-abelian degrees freedom there, then you actually may be able to understand all the macro states of the black hole just from really somehow those five branes somehow, which is that the picture?
That's really the picture that as I say, this was something that was Callan Maldacena, Das Matur, Armando Varia. There were people that studied the absorption and emission from some kind of effective string, treating it as a free string. Right. So really the question is, to what extent is this little string approximately free? That certainly accounts for the entropy. It seems to account for the near BPS gray body factors of absorption and emission. And what I'm sort of suggesting here is, can I shove all of that stuff that was done 30 years ago down the throat and still have something that works?
Right. Can you also? Yeah, I'm not sure I understand precisely this breathing mode dynamics. Can you say? Yeah, maybe I forgot about this precise.
It's just this picture. As I let the 5-brane throat breathe up and down, the throat goes up and down.
Yeah, but what controls that? Somehow, what is the dynamic mode controls that?
It's the mode that rescales the source.
Yeah, but from the point of view, say from the string or Brane point of view, what would be the is the fluctuation?
So this would be adding a small amount. So adding a right moving excitation and then coming. If I absorb a graviton, right? So the throat, of course, is governed by bulk gravity. Bulk gravity is coupled to these branes. Okay, so it's going to the breathing mode of the sources is also going to be coupled to some graviton modes in the throat. But if I absorb a graviton onto a string, it becomes a pair of left movers and right movers. So it's just adding a left mover and a right mover on top of the gas of left movers that's already there. It's the same picture as from 30 years ago.
Yeah, but
I just want to understand somehow whether there's a sharp way to isolate this mode in the simple language.
Yeah, that I don't know.
Okay.
I mean, to me, it looks like it does couple to all sorts of other crap.
Oh, so just following up on that, I think there should be a way to isolate it, and basically because everything here, these rescalings you're doing are awfully close to just being a pure gauge rescaling, that you're basically doing a diff on your x's. I mean, what set the scale of x in the first place? And therefore, I think that this is something it should be a large gauge transformation. It's something that, to a first approximation, is a symmetry. And in fact, it's not just merely a symmetry, it's a gauge symmetry. And then, however, to the next approximation, it's not. And that's what should set a scale difference and create a gap.
I'm not sufficiently up on the literature on quasi-normal modes and ADS2 and all of this. I mean, that's on my study list. One thing I should say is that people have studied in the superstratum literature. These are nice separable wave equations there, and so one can ask what is this complete spectrum of scalar wave modes in the superstratum throat? That's been done, and it's more than just the Schwarzian mode.
And no scale separation.
Not that I can tell.
In your discussion of the adding the near BPS excitations, maybe the question is, how important was it that you were very close to the BPS bound? Because in the comments about the Schwarzian mode, the coupling of the Schwarzian theory is always related to this thermodynamic breakdown scale. But the fact that the length of the throat stabilizes, at least based on our 2020 work with the LSU and Turiachi and Zhao, I mean, that's a strong coupling result that comes from Gravitino zero modes and stuff like that. At least from the formulas you wrote on the slides, it didn't necessarily look like it was that, didn't depend on that very sensitively, right? If you did this LMRS story, but you dropped fermion superpartners, then the length of the throat doesn't stabilize quantum mechanically. So I know that you're starting from the point of starting with a BPS solution and adding the excitations, but how important to the physics was it that you really had something supersymmetric to start with?
I don't think so, because even when you're non-BPS or you're not in the BPS sector of the supersymmetric theory where there are index states, there's still this, what I would call a quantum scale, some scale of thermodynamic breakdown.
Yeah.
And so I regard that as being some kind of a stretched horizon scale where quantum gravity effects are becoming important, and that's always some finite depth, right? It's basically you're asking where is the energy of an individual Hawking quantum equal to the available free energy above extremality.
That's true whether or not we're talking about SUSY or string theory or anything like that. But I think this statement that the throat stabilizes and you have a large number of extremal microstates is from this Schwartzian point of view, it's highly sensitive to the amount of SUSY you have. And your argument, at least as presented here, didn't seem like it well, maybe it did, but I guess that's kind of what I'm asking.
Well, I mean, everything I'm doing here is embedded in some 4-4 supersymmetry.
Yeah. And actually, the LMRS paper is technically only n equals 2 SUSY, so you really need an n equals 4 version of the result, but it should be the same.
I ran out of space on the slide, but I know you guys did yeoman's work on all this near BPS thermodynamics. So yes. Absolutely.
Okay, if there are no more questions, we'll thank Emil again. We'll go for a coffee break. We'll meet back at 10:45.